Hello everyone, welcome back to Math with Allison. Today we're working in our integration series, so we're going to be talking about improper integrals and what happens when we have an unbounded integrand. So let's go ahead and dive into it. Here we already know what an improper integral is, and it's when we have infinity or negative infinity in the integral. So the issue with this is when we take the antiderivative, we always plug in upper minus lower when we want to solve it, right? So when you plug in infinity, infinity is not a number, so you can't just like plug it in necessarily, which is why we have to write it with a limit. But there are other ways that we can have improper integrals, and that has to do with, well, what if I change the integrand right here? So instead of from 1 to infinity, I have from 0 to 1. One of those bounds is an issue, and it's 0 because you can't plug in 0 to 1 over x squared. That's undefined. So this is where we have an unbounded integrand, and here we're going to look at what's the issue. So we have that 1 over x squared is undefined at x equals 0. So here is the normal integral that we looked at in our last video, right? We take the limit as b approaches infinity and we replace that. So we have 1 to b of 1 over x squared dx. So b, as we can see, is going off to infinity, and we can see that our function gets so close to the x-axis that it's not going to add any area anymore. But what were to happen if we were to look at it the opposite way? So instead of going from 1 to infinity, we went from 0 to 1. Well, we would have to rewrite this as a limit as c approaches 0 from the right side, right? We're approaching from this right side of our integral from c to 1 of 1 over x squared dx. So what we're doing now is we're accounting for this entire integral. So let's go ahead and try to evaluate this. I rewrote it as x to the negative 2 so we can really see power rule going on. So here we have the limit as c is approaching 0 from the right side. And here what we get is negative 1 over x, right? I add 1 to the exponent, I get x to the negative 1 divided by negative 1, which we can rewrite as negative 1 over x, evaluated between c and 1. So that's why we have to rewrite it as a limit, is because we cannot actually plug in 0. It's undefined. So we have to take the limit as c approaches 0. So this is going to be negative 1, and that becomes plus minus a negative 1 over c. So let's go ahead and talk about what happens. If I were to plug in 0 to 1 over c, so 1 over 0 to the right side, this is going to get really big. It's going to blow up, and it's going to approach infinity, which tells us that this limit is going to equal infinity. So why is this one an infinite area? Well, it's true that 1 over x squared is going to get really, really close to our y-axis, but our area is not going to be this tiny little region. It's actually going to be this entire length, which is going to start getting really, really big, right? So this is saying that it doesn't get close enough to the y-axis that the area is so little. It's going to continually be adding area this time because it does not get close enough to the y-axis. So here we have an example of an infinite one, and it's okay for our answer to be infinity, right? It makes sense for that to have an infinite area. So let's talk about the different types of improper integrals with unbounded integrands. So first we have the one that we just did. We have that the limit as x approaches a of our function is going to be infinite. And so that means we have to replace our lower bound with c, which is approaching a from the right side. And we can see our function, what is happening here, the area that we're accounting for, and it's just like the example we just did. So let's talk about a new one. So this is going to be where our function is approaching b from the left side, and so this is going to be our upper bound, is going to grow infinite. So what we have to do is replace our upper bound with the limit as c approaches b from the left. And so here we can see why we're approaching from the left. Let's pretend that the y-axis is going to be our b. We're taking the limit as c approaches b from the left side because now we're trying to account for that entire area. So that's a nice visual for it. There's one other type, and you can probably guess it. This is going to be where our function is undefined, somewhere between our bounds. So here we have the integral from a to b, and what happens is we have some undefined value in between a and b. So I labeled it u, undefined, or something else, I don't know. And here what we have to do is we have to replace both of them. So first we have the limit as c approaches u from the left side, and that's going to be our upper bound. And we also have the limit as d approaches u from the right side, and that's going to be our lower bound. And here you can use any letter. You don't have to use c, you don't have to use d, you can use any letter, right? Literally just a random one we came up with. So here we have f is continuous on a to b except at that undefined value between a and b where f is unbounded. So you can think of u also as unbounded, right? So let's go ahead and talk about how we're going to do some of these problems. Here we have the integral from negative 3 to 3 of 1 over the square root of 9 minus x squared dx. So notice here, where is our function going to be unbounded? Well, we have this function is unbounded, or you can think about it as undefined, whichever way your brain likes to work. And this is going to be at both -3 and +3, which is going to be both our bounds. So here we're dealing with two types of unbounded integrams. But what if I told you that we can cut it down to 1? This, using symmetry, is just going to be 2 times the integral of 0 to 3 of 1 over the square root of 9 minus x squared dx. You can evaluate either one of these, and both of them are totally going to give you the same answer, so whatever your heart desires. So let's go ahead and now rewrite this so it's going to be a proper integral. So the limit as c approaches 3, and this is going to be from the left side because we're going from 0 up to 3, so it's going to be on the left side of 3. Here we're going to fill the rest in, so 2 times the integral 0 to c of 1 over the square root of 9 minus x squared dx. So let's go ahead and take that antiderivative, right? We know what this is going to equal. This is going to be inverse sine of x divided by 3. 3 squared is equal to 9. And this is going to be evaluated between 0 and c. So let's go ahead and plug in upper minus lower. So here we have inverse sine of, that's going to be c divided by 3, minus inverse sine of 0. But that, inverse sine of 0 is just 0, so we don't have to worry about that. So let's go ahead and see what happens when we approach 3 from the left. If I plug that in here, that would end up being 3 divided by 3, which is 1. So this is going to be 2 times inverse sine of 1, and that is the angle at which sine is equal to 1. So think about it at the graph. We start at the origin, and we go up to 1 at pi over 2. So it's going to be 2 times pi over 2, which is equal to pi. And so here, even though that we have an unbounded integrand, we can still find a finite area. So let's see what this looks like with the visual. Here we have the graph, and we have our two bounds. And so we can see at some point, our function is going to get so close to its vertical asymptote that it's not going to add any area anymore. And so we can say that this infinite area is actually finite. We can actually find value, and it's going to be equal to pi. So area is equal to pi. Let's go ahead and try one more here. We have the integral from 1 to 10 of dx x minus 2 to the 1/3. So notice here that our integram, the actual values, neither of them are going to be an issue. I can plug in 1, I can plug in 10. There's going to be an issue value in between. So this function itself is going to be undefined or unbounded. And 2, that's going to be between our two bounds. So we need to go ahead and split this up into two integrals. First, it's going to be 1 to 2 of dx divided by x minus 2 to the 1/3. And then we need to add the integral from 2 to 10 dx divided by x minus 2 to the 1/3. So now we want to rewrite these as proper integrals because we can't plug in 2, right? 2 is undefined. So we're going to take the limit, and I'm just going to say c is going to approach 2 from the left. Remember, we're starting at 1 going up to 2, so that's going to be the left side of 2. And here we have the integral from 1 to c, and we can rewrite this actually, x minus 2 to the negative 1/3 dx. So that way we can really see power rule. And here we're going to add on, let's take the limit, and you can just, like I said, you can choose any letter. Literally doesn't matter. But as d approaches 2 from the right side now, right, because this is going to be d, this is going to be 10. So we're starting at 10, and we're approaching 2. So I know it's from the right side. And again, I'll just rewrite it, x minus 2 to the negative 1/3 dx. So let's go ahead and evaluate these integrals. We have the limit as c is approaching 2 from the left. And this is going to be, I'm going to add 1 to the exponent. So that's going to be x minus 2 to the 2/3, and then I divide by the exponent, or I can just multiply by it flipped. And that's going to be from 1 to c, and I'll fill in the other one the same way. Our next step here is to plug in upper minus lower, so I'll go ahead and do that. Alrighty, I got those both plugged in, and now we're going to go ahead and see what happens. So first, we're going to approach 2 from the left side. If I were to plug in 2 right here, I would be approaching 2 minus 2, which is equal to 0. So actually, that first term goes to 0, and then we have minus 3 halves. And I'm going to rewrite this so we have the cube root of negative 1 squared. And then let's go ahead and talk about what happens when we plug in d. So it's approaching 2 from the right side. So this is approaching 2 minus 2, which is again approaching 0. So here we're going to have plus 3 halves, and I'll rewrite this as a radical as well. The cube root of 8 squared, and that's going to be minus 0. So that's going to be super nice. Those are just going to go to 0. And now we can go ahead and evaluate this. So 3 halves times, that's going to be negative 1 squared, which is just positive 1, plus 3 halves. The cube root of 8 is 2. 2 squared is equal to 4, so that's going to be 4. And don't forget that minus there. I almost forgot it. There's a minus right here. So here, that's just going to be 3 times 3 halves, which is equal to 9 halves. So again, we got a finite area. So they don't all have to be infinite. They don't all have to be finite. So let's go and see what this looks like with the graph. We can see here we have that vertical asymptote at x is equal to 2, but our function gets so close to the vertical asymptote that's not going to add any area anymore. And so we got this entire area that I highlighted in green is equal to 9 halves. So that's all I have for us in this video today. If you enjoyed it, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.